All right, I think we should probably get started slowly. Um, anyways, I'm very excited for everyone joining in here. We have people from both teams, from the Cartesi side and the Espresso side. We might have a few more people joining in the audience as well in the next couple minutes, but I think we should probably get started. Anyways, welcome to this research and design call with Espresso. We had one in the past. But in the meantime, we've already had some cool integrations happening with Karsten working on this famous Rickroll demo that we will get into during this call. For the structure of this call, we want to kind of make it similar to our game building calls for those familiar. But basically, we will be having a conversations with the speakers from both sides, and welcome input from the audience at all times. So feel free to jump on stage with your questions, or obviously ask them in the chat if that's preferable for you. Yeah, without further ado, I think we can get started with some short introductions. Maybe Curry and Benedict, feel free to introduce yourselves first.
Yeah, sure. Hi, everyone. Great to be here. My name's Jeb, Curry Howard on Discord. I'm the lead engineer working on the Espresso sequencer. And yeah, I'm really excited to get into the weeds of how Cartesi is integrating onto our stack. Benedict?
Yeah, hey everybody. I'm really excited to be here. My name is Benedict Prince. I'm the chief scientist and the co-founder of Espresso Systems, who work on kind of the academic research side. And I'm also a professor at NYU in cryptography.
Awesome. Carson, you also want to give a short intro?
Yeah, so I'm just yet another Cartesi community member who has been hacking around quite a lot with Cartesi technology, and also a grantee who's also part of the Cartesi Foundation as a board director. And I've been playing around quite a lot with kind of like the Espresso integration.
Awesome. Super cool. So maybe we can start introducing each other's projects. And I was thinking, we tend to have a lot of jargony words, and the lingo can get quite complex in this space. So if possible, if we can try to explain these projects from in more simple terms. I know it can be very difficult to do that because the jargon is there for a reason, right? But maybe we can start with kind of Carsten introducing Espresso. Actually, I'm curious, Carsten, if you could kind of give your perspective on things, and then Benedict and Curry, you guys can add, and fill in the blanks.
Sure. I guess I can start with Espresso. So explaining each other's projects. Let's start out with that Espresso is awesome. Let's start there. And what they do is to provide a solution to what we in this industry call the data availability problem to some extent, that there's a lot of space needed in order to kind of like have transactions transmitted out to the world, so everybody's kind of like up to sync. And on Ethereum, as you know, there's limited amount of data you can send through, for example, as you've been seeing with, for example, with spiking gas prices and so on. And it quite limits the kind of like the different applications that are possible to do using blockchains and rollups. And what Espresso does is provide two things, which is one is to kind of like broadcast the data out in a very fast fashion, and then verify that this data actually made it out to the nodes that are part of the network. And then at the same time also putting an order to the transactions that come in and kind of like put them in a block. So there's a certain sequence to it as well. Yeah, I think that's kind of like the short notion here.
Awesome. Benedict and Jeb, anything to add?
Yeah, thanks, Carson. You should do sort of all of our announcement. I mean, yeah, I think this is exactly right. I think at the heart of it, it's a sort of scaling solution, or part of a scaling solution. It's called a decentralized sequencer. That's the jargon word, or a decentralized shared sequencer. And what it does is it works with these rollups, and these rollups have a lot of transactions and a lot of data. And one key challenge for these rollups is to even say what transactions are included and in what order, and how can everybody read these transactions. And essentially, at the heart of it, Espresso provides answers and solutions to all of these questions. So it is a decentralized protocol that orders all of the transactions and makes sure that everybody has these transactions available. And one other feature, sort of that is sort of more the long-term vision of it, is that actually many rollups can use the shared sequencer, and so today it provides sort of a scaling solution and a decentralization solution, but it also in the future, in the very near future, hopefully, will provide an interoperability solution. So this means that if multiple rollups are using this shared sequencer, then it makes it significantly easier to for example, move assets from one rollup to another, or build interoperability solutions between these rollups. So that's kind of the more far out thing that I'm very excited about.
Very cool, very cool. Yeah, I think we will be able to drill down into some of these things a bit more in a few minutes. Maybe Benedict and Jeb, one of you guys can try to also kind of give your perspective on Cartesi, like kind of how you understand it. That'd be great.
Yeah, I'd love to. So Cartesi is super cool. At a high level, it's, as I understand, basically a toolkit for allowing developers to build and deploy application-specific rollups. So essentially a scaling solution. Instead of writing you want to write a decentralized app, but you don't want to deal with some of the problems of deploying that app as a smart contract on, say, Ethereum. Problems like having to compete for block space with other apps, having to compete for processing power with other apps. So Cartesi makes it really easy to write this app and run it yourself as its own app chain, whether that be a sovereign rollup or a layer 2 or a layer 3. But the really, really cool thing is that the platform that you build this app on is not one of the typical sort of crypto or Web3 specific virtual machines like the Ethereum virtual machine or Solana virtual machine. Instead, Cartesi lets you develop your app on a general purpose RISC-V machine, which is just it's like a virtual, a PC essentially. And you can boot some off-the-shelf operating systems. So you can boot Linux, and then you can use all of the standard Linux tools and programming languages to develop your decentralized application. And it kind of frees you from some of the limitations and rough edges of working in like Solidity and these like Web3 native tools. So I think that's really, really cool for developers and sort of empowering the space of applications that can be built in a decentralized way.
Awesome. Yeah, thanks, Jeb, for that great explanation. Carsten, anything to add from your side?
Not particularly anything really to add. I think Curry nailed it quite well. I think it's what I really like about Cartesi is the fact that I can sit down, I can prototype up something in JavaScript, and you run it inside Node.js and Cartesi, combine it with something like Espresso, and it actually works.
Yeah, no, that makes sense. As a next step, I was thinking if we could drill down a little bit more into Espresso, and I think Benedict, you already gave a great overview. But so we have this shared and decentralized sequencer, and I was wondering if we could kind of dive into both components. So maybe first on the decentralized side, why do we need this, component, this piece of the stack to be decentralized as well?
Yeah, so that's a very good question. So to reiterate what a sequencer is and kind of what alternatives are to a decentralized sequencer, it is literally the piece of software that decides. So rollups take a set of transactions and then either using fraud proofs or, there's also ZK rollups, which is zero knowledge proofs. Basically, they prove that, these transactions were executed efficiently. And you might say that, like using fraud proofs, for example, that the idea is that, some server can do this and you don't have to trust that server anymore because you have these fraud proofs. So if they misbehave, then you can still catch them. The problem is that if you allow a centralized server, like let's say we have a rollup server, just a single server, that now executes the transactions. The problem is that server still has a lot of power, because what it can do is it can decide what transactions are included and in what order. So for example, it can censor transactions and can say, oh, this transaction can be included or this one can't. Or then for some DeFi applications, there is, some sort of front-running mechanisms where, now the centralized server has a lot of power to front-run applications. And, it kind of creates more of a Web2-like environment where we again have to rely on central parties and also single points of failure, right? Even if that server is not malicious, if it goes down, the whole system fails. So the idea is that we want to decentralize this component, and that is exactly what Espresso is building or has built, is a decentralized sequencer, which means it's simply a large set of nodes. This can be like up to 1,000 nodes. And they basically do the ordering of transactions. And as long as a majority of them is honest, then that no single party basically has too much control about the ordering, and it's impossible to censor transactions and all of the good properties that we want from decentralized protocols. So this is why it's really important to decentralize the sequencer.
Great.
Can I add one more thing to that?
Of course.
So that there's sort of one more kind of power that the sequencer has that I think is really important to keep in mind, and that we don't want to put in the hands of a centralized party. So Benedict talked about how the sequencer has the power to exclude transactions or reorder transactions. But there's also another thing that many rollup sequencers do, which is they provide what we call a pre-confirmation. Basically, in many designs, the rollup state is ultimately determined by transactions being posted to L1. But the sequencer will tell you ahead of time that it promises to include your transaction in a particular block. And that kind of makes sense. Like, the whole point of using a rollup is to get faster execution than the L1. So why would you want to wait for your transaction to get posted all the way to the L1 before getting a confirmation that it's been included? But if you allow a centralized sequencer to do this, it can basically lie. It can say, like, sure, I've received your transaction and it will be included in this upcoming block. But then when it ultimately writes back to the layer one, it could simply not include that transaction. And this is kind of akin to like a fork or a reorg on a traditional blockchain, where like you got some sort of confirmation that your transaction is included, it was included, and then it wasn't. And that's almost like a loss of funds, or can lead to double spends and things like that. So another advantage of decentralizing the sequencer is we can make the same promise that a particular transaction is going to be included in an upcoming block, but now that promise can be guaranteed by, thousands of different nodes participating in a consensus protocol with some kind of honest majority assumption, instead of having this guaranteed by just one single trusted server.
Very cool, very cool. Yeah, so we can unlock some new interesting affordances. On the shared side, Benedict, I think you already touched on some good points, but maybe Jeb, you can also discuss, like, kind of on the shared sequencer side, like the shared aspect of things. What are some cool things that you think this can unlock?
Yeah, I think Benedict really nailed it earlier with just one word, which is interoperability. And maybe this is especially important in the context of like Cartesi and app-specific rollups. Right, so when I kind of introduced Cartesi earlier, I said like the the advantage of doing an app chain or an app specific rollup is you kind of get away from the congestion and the cost of running your app alongside, thousands of other apps on Ethereum. But there is a big advantage to having all those apps running on Ethereum that we don't want to lose, which is that if all of these apps are just smart contracts on Ethereum, it's really easy for them to interoperate with each other. Users can move liquidity around between apps. They can sort of compose different apps together. So in this sort of rollup centric vision for the future, where there's, instead of 1,000 different apps, now there's 1,000 different chains. We need somehow to retain the interoperability between these app chains, and the sort of existing solutions for interoperating or sharing tokens between different rollups and different blockchains are not good. Like we have bridges. Bridges are often custodial, or they're really complex and subject to hacks, or they have long latency to move things around. So it's not nearly as seamless as just two smart contracts interacting on Ethereum. So what we hope to do with Espresso is to make it, by virtue of having all of these different chains and rollups sharing a single sequencer, to kind of recover that shared layer that allows liquidity and information to flow between different apps really quickly and simply. So we can kind of we can get really deep into the weeds, however much you guys want, about how this works. The basic high level kind of superpower that a shared sequencer gives you is the ability to build a block for multiple rollups at the same time. So if there's 1,000 different rollups all using the Espresso sequencer, I can build a single block that is included atomically in the sequence of transactions, and includes transactions for each of these 1,000 different rollups. And so I can do things like within a single block, swap tokens between rollups, or have one rollup send a smart contract call to an app running on another rollup, and sort of things like that.
Very cool. Very cool. Yeah. Maybe could you touch on kind of the different sequencing solutions that exist? So maybe starting with, you briefly mentioned already, maybe you could use, for example, L1 for ordering and data availability, right? I think we call this, correct me if I'm wrong, this based rollup architecture. Maybe Benedict, maybe you can kind of explain the trade-offs of such a solution.
Yeah, exactly. That is exactly a based rollup, and it is especially for data availability, which is just the aspect that even if you have a centralized server, or in any rollup architecture, sort of people are aware that you need to make the actual transaction data available, because if the transaction data is not available, then essentially the entire security of the rollup breaks down. And a lot of rollups today use L1 for that, and you can also use L1, for the sequencing, for the ordering. And it actually has some good properties, right? It's, the L1 is incredibly secure. It's, it could act as a shared sequencer if multiple multiple rollups use the same L1. It provides sort of high data availability guarantees. There's only one problem with it, and unfortunately it's a massive problem, which is that it's crazy expensive. And it's crazy slow. We have really, really slow latency, right? The number, there's only one block every 12 seconds, and then you might not even be able to push your data onto the block every 12 seconds. So I think rollups now push the data in more like 10-minute intervals. So you have basically a 10-minute window in which you don't have any data availability, and nobody can really verify things, and that massively slows down the process. So what we basically want to provide is a solution that has the same or very similar security properties to using a based rollup, but has on the other hand, right, like just to contrast this, if you use a centralized sequencer, the centralized sequencer can be incredibly fast, right? That's just a server, running some software. There's going to be very minimal latency. Everybody just sends their transactions to that server, and it can sequence things. And if you use something like Arbitrum or Optimism today, that's essentially the architecture that they have. And one of the really nice things, and one of the reasons why people use these rollups, is because they're so fast and provide cheap transactions. And with Espresso, we're really trying to build the best of both worlds. So we're trying to have the same kind of security or very similar security as a base rollup, but we're also trying to retain the speed and the sort of 1 second or sub-second latency of a centralized sequencer. And I think sort of with cool deployments and showing the things and building the things, like pushing videos on the sequencer like Carsten did, this is it shows you the power of our architecture and how we're basically achieving this vision of having an ultra scalable software design built by Jeb, and amazing work that our amazing engineering team is doing, together with, also still having the decentralized component and having strong security guarantees.
Very cool, very cool. Maybe we can quickly touch on the security guarantees. I think that's a big point, right? A lot of other solutions are kind of bootstrapping their own networks. I'm curious about the trade-offs there and how you guys are approaching it.
Yeah, I'll start with some answer, but Jeff, if you want to add to it, then please do.
Yeah,
but
sure.
I mean, in general, we're building a proof of stake network, or the Espresso sequencer is a proof of stake network, which means that the security guarantee essentially relies on, roughly speaking, if 2/3 of the staking set is honest, then the network is secure and is basically gives you these safety and liveness properties that you want. There is, this is the very high level overview, and there's a lot of details and a lot of thought that we put in to, how you can actually strengthen those guarantees or give them more meaning. And one of the core things that we're planning to do is that possibly, or at least for a lot of components, right? Ideally, the question is, 2/3 of what set, right? So there will be some Espresso token, and if the idea is that say we want that 2/3 of this Espresso token, or people who are holding this Espresso token is honest. The problem is that maybe in the beginning, that is not actually that meaningful of a guarantee because the token isn't as established or for whatever other reason. So one question is, ideally we would actually have I said we want to have the same guarantee as a base rollup. And what this would mean is that ideally we would want that the nodes running our system are the same nodes as they're basically just Ethereum nodes. So if we could say that, for example, our system is secure as long as 2/3 of the Ethereum nodes are honest, then we would have there would be likely a much stronger guarantee. And it turns out that if we use what is called restaking, then we can actually achieve such a guarantee. So, how exactly we do this is a little bit, more complicated and goes into details. But essentially, the idea is that, say, we require that Ethereum nodes can restake their Ethereum token or their ETH. What this means is that they both, if they choose to, they can run both the Ethereum software, but they can also run the Espresso sequencer software. And then they basically sign off on blocks. And what we can see then is that if, most nodes will do that because they will get some additional reward, and then we can basically guarantee that that espresso blocks, or that espresso sequencing, that the espresso sequencing, has strong guarantees, because it basically receives signatures, or 2/3 of the Ethereum stake also signs off on these blocks. And architectural designs like that, and many other designs that we're thinking about, and the way that we, for example, do data availability, allow us to have very strong security guarantees, but while we maintain sort of our high throughput and our fast network design.
Okay, very cool, very cool. Yeah, so you'd say the focus is really on trying to replicate, sort of, we get as close as possible to sort of L1 security, but while while being decentralized and offering like the high throughput and stuff like that as well.
Exactly. The idea would be sort of the ideal solution, or the target that we're aiming for, is that even in the kind of the node requirements that we set, is that we can have the same or almost the same security as Ethereum, while having much higher throughput and lower latency. And all of our architectural designs are sort of basically use exactly those two goals, are designed with those two goals in mind.
Awesome, great. I want to get into tiramisu a bit. Maybe we can jump back a bit to that later. But Karsten, I'm curious if you could do a short recap of the current Cartesi stack, and how is sequencing basically done, like pre-Espresso?
So with the kind of like the current Cartesi rollup stack, it's basically like how, let's say, traditional rollups have been working. They're posting the transaction as in the input to the rollup, essentially to a layer 1 EVM typically, or to a layer 2 as well as it could be, for example, like arbitrum optimism, and basically having kind of like a typical, let's say, centralized sequencer, while still being able to kind of like send transactions as well, so on chain. And it basically means to Cartesi that there's a very strong restriction in kind of like, let's say, the size of the inputs, or the size of the transactions, and everything that we kind of need to put on chain is kind of like very easily becomes quite a high price for kind of like for people to maintain rollups. And if, let's say, that you're doing, for example, like a chess rollup or something like that, the cost might basically be prohibitive. And what I like about something like Espresso is the fact that there's kind of like two things here. One is that it's kind of permissionless, as in that I can essentially start posting transactions to a rollup without deploying a smart contract. That's the kind of like the first thing here. So I define a rollup as it that starts at a particular Espresso block, essentially, and I can then take all those transactions, come in, process them together, and I can kind of end up in what's the current state of my rollup. So I don't need this whole, let's say, deployment and maintaining and so on to kind of like have an active rollup, which is very useful. When I then want to actually, let's just start bridging this into, okay, let's say, having Ethereum blockchain know about it, then that's when I then would start doing, for example, the typical verifiable computing and analyzing the data availability of the information dispersal proofs that, for example, Espresso is doing. And I think I think basically that all the crazy things that we're talking about blockchain back in 2016, 2017, when Ethereum was like extremely hot, and people tried to do them, and sorry, and basically found that the gas prices were too high, was not affordable, or too difficult for people to start using. it's basically what I think that we'll see that Espresso combined with Cartesi will allow us to do.
Awesome. Yeah. You mentioned verifiable information dispersal proofs. Could maybe one of you guys, maybe Benedict or Jeb, could one of you guys kind of explain that concept? Karsten, if you want.
I can take a shot at it. So yeah, Max, you hinted at tiramisu earlier. So for context, tiramisu is our data availability protocol, the part of the sequencer that responsible for guaranteeing that the transactions you put through it don't get lost. And the architecture of this protocol is it sort of has three layers. And from top to bottom, the layers go from like fastest but most likely to fail, and to the bottom we have sort of our fallback layer, which is like slower but guaranteed with very high security guarantees, and that's the verifiable information dispersal layer. So essentially what we do is whenever a block is sequenced by the Espresso sequencer, the proposer, whoever is sort of producing this block, does a bunch of complicated math and essentially turns this one big block into thousands of very small shards. And there's redundancy between these shards. So the property that you have is, the total size of all of these shards is not much bigger than the block itself. Like maybe it's a factor of 2 bigger or something like that. But if you have, say, any 2/3 of these original 10,000 shares, you're able to reconstruct the original block in its entirety. So you get this kind of redundancy. And then the way that you essentially just guarantee that this block is persisted is just send one of these shares to each consensus node, along with a cryptographic proof that the share was kind of constructed with this correct redundancy property. And then it dovetails right in with the kind of honest majority assumption that underlies the security of the whole consensus protocol, right? So we're already assuming that of these 10,000 nodes, at least 2/3 of them are honest. They're going to participate correctly in the protocol, which means that at any point in the future, we can find 2/3 of these nodes that are honest and willing to give us back this cryptographic shard of data that they received. And if we can do that, then at any point in time, we can reconstruct the original block. So yeah, essentially what this allows us to do is replicate a potentially very large block among many participants, but each individual participant only receives a small amount of data. So the amount of storage that you need to run a node and the amount of bandwidth that this protocol consumes in the network is proportional to the size of the block, even though we're kind of fanning out over 10,000 participants.
Yeah, I think that's also one important thing to kind of like keep in mind in general with like this kind of like data availability solution is that compared to a blockchain, like you can mostly expect that people are keeping around the data that's being published, while with something like a data availability solution, you can probably assume that, let's say that when something has been broadcast, that then people will have it, but there's no, let's say, promise from something like Espresso that you're going to keep all the data available forever, for example. So when, let's say, blocks are published and we have, let's say, data, it's also, let's say, the responsibility for the rollups to have some kind of system where they're kind of like archiving, let's say, the old blocks as well, I presume.
Yeah, that's a good point. So the main property we're trying to guarantee with Espresso is that the data is available long enough for all the rollups to get it. And then at that point, as Carsten said, the rollups can decide how or whether they want to persist that data long term.
Awesome. Great. By the way, anyone in the audience, again, if you have questions, please drop them in the chat or jump on stage. As a next topic, let's get to the Rickroll demo. Carson, could you give a bit of an explanation of what you built and how you came up with it and what it all means?
Yeah, so for good measure, it wasn't only me building it, but also other members from my team building it for good measure. But basically, we had gotten the capability to like synchronize and gather transactions and blocks from Espresso, and I was kind of like discussing with you, Max, here, that what's possibly the craziest thing that we can do that is completely impossible with the existing solutions, like let's say with the VM block space or even computation, that shows kind of like the unique properties of these two systems. And basically, if you're also looking at a little bit of history, like video has traditionally been kind of like considered the big bandwidth thing that people have been sending through systems as new, let's say, technologies came out for broadcast or let's say fiber connections and so on. So it was quite natural for us to kind of like see that, okay, let's try to put video through Espresso sequencer and seeing if it can take it, which it can. And at the same time showing how like it can build something that would be so mind-bogglingly difficult in either in WASM or in Solidity to try and decode actual, let's say, video inside a blockchain or rollup VM and actually visualize that on the node as well in ASCII art. And it's a fantastic showcase. The original video was not actually Rickrolling, but it's also a classical inside one. We were actually supposed to show Vitalik clapping video, but it didn't render as well in ASCII art as we actually wanted. So yeah, that's basically how the story kind of came around, that we wanted to make this actual, let's show something that's completely impossible to do today, to actually show how does the future of rollups look like.
And one thing that's cool, Carsten, like correct me if I'm wrong, but you didn't ask anyone for permission to do this, right?
Exactly.
This is like, I mean, this is the cool thing about, I guess, the entire world, that we're building here, is that, sort of, Carson, you just did this, right? Like just built this and, you use the software that was out there to run this. And there was no, there's no permissioning, no, like this was a feature that didn't exist, right? Like nobody before had done something like this. And just by writing some software, and now, you can sort of Rickroll the Espresso sequencer. And yeah, it was a really, really amazing demonstration. I was like, very impressed by it. Like, super cool.
Yeah, as you guys called it, like I'm all here for the permissionless Rickrolling. This is what the internet was built for.
Exactly. That's the unicorn land.
100%. No, super cool. What was it? A 17 megabyte video?
Yeah, something like that. I mean, you would be waiting for a couple of hours before they could post it to an Ethereum block, for sure.
Yeah, I'm paying like thousands or tens of thousands of dollars in block space, right? Like,
what would be the estimate here, Benedict? Do you have any idea of the numbers?
I don't, but like, what's the block size? Is like, I think a block is like at most a megabyte roughly is the target block size in Ethereum, and I guess 17 megabytes. So that's 17 blocks that you have to completely fill yourself, and like there can be no other single transactions in it. So yeah, I don't know.
Well, it would be art, that's for sure, but also expensive art.
Would be very expensive. Yeah.
Do you have a feeling about how much it would cost to send broadcast 17 megabytes, like just completely theoretically through something like Espresso sequencer?
Oh, through Espresso. Yeah, I think it really depends. I mean, I think that it really depends on, of course, how much competition, like even in Espresso, same as in Ethereum, it depends on, how much congestion and competition there is. But especially in the beginning, I think that we can, sort of the data rates that we target are in the, I don't know, let's say 10 to 30 megabytes per second. So, this only takes like a second of block space. So it really is like, unless the entire world starts sending, massive videos over the Espresso sequencer, then, the block space will be, there will be so much block space, so much more than even possibly demand, that I don't think this will have very significant costs. Like this could be, I don't know, I'm just completely throwing out numbers here, but in the cents, or like low dollar amounts, of course, right? Like if suddenly we have applications where we have that use a massive amount of block space, then there will be some competition for it, but I don't really see that happening, especially in the beginning.
Yeah. You mentioned like having to spread this video file across like 17 blocks on Ethereum, and on top of that, Ethereum has what, a 12-second block time. So that's you're talking about tying up like the entire block space of the Ethereum network for a period of several minutes in a row, versus like on Espresso, theoretically, this could be like half of the available block space within a 1 second period. So it's orders of magnitude less detrimental, I guess, to the overall network in terms of how much of the available bandwidth is being consumed.
Yeah, I think we calculated that Espresso might have like a factor 100 to 300 more block space than Ethereum has.
Yeah.
So, like prices are, this is like not a perfect price demand curve, but like, you can assume that they're also that order of magnitude cheaper, like 300 times cheaper, but probably actually even way more. Because those relationships are not necessarily linear.
Right. I mean, the data is effectively free up until you hit that saturation point. So depending on how much demand there is, it might be the marginal cost of like more bytes might be nothing. At least you could do a lot more before you hit that point.
Mm-hmm. Right now, the shared sequencer, it's like shared between, it's like one shared sequencer, or could you have like multiple shared sequencers? So you would have like kind of different fee markets and costs depending on the applications that share a specific sequencer. I suppose that's also an option, right?
No, I mean, the idea is really to have one shared sequencer, which is also why it needs to have so much capacity. Because that really opens up like that really helps with the interoperability. The second you have multiple shared sequences, then they're not shared between each other anymore, which sort of then means that there's not the interoperability aspect anymore. But yeah, this is why we need sort of this high throughput, is because we do want to sort of have many rollups run on the same shared sequencer.
Okay, makes sense.
But yeah, a lot of rollups are not going to push videos through that.
Yeah. Maybe Carson, do you want to touch a bit on the steps of the integration, your learnings along the way, if you faced any challenges?
Yeah, I think kind of like initial challenges as such, much more like kind of like trying to bring up the, let's say, the local host environment for the sequence and so on. We had not like identified correctly that there was a working test vector we could be using. But Espresso API and documentation is fantastic in that way, as it provides very nice Rust APIs for kind of like connecting in stuff like listening to blogs, having all the data structures, getting, let's say, incoming transactions, checking if they're for your actual virtual machine ID. And it was surprisingly nice to kind of like work with. Of course, this is kind of like what we were experimenting with doesn't yet kind of like include layer one integration, but it is my understanding that kind of like that because of the way that Espresso is also dealing, for example, with, let's say, with restaking and posting to the layer one and aligning with it, it becomes basically quite easy to kind of like integrate even, let's say, a fraud proof on top of it. It's something where I now use this also as a benchmark when I'm looking at different data availability solutions, seeing is this good enough docs, is good enough APIs. And I think the learnings was that when you don't have to build your own sequencer, life becomes so much easier. And definitely if you don't need to build your own data availability solution, life becomes a lot more easier and kind of like focus on what you actually want to build with your particular virtual machine and rollups framework.
Nice, yeah. Very cool. Yeah, maybe we can dive a bit deeper into like what's next. So what does the future look like in a world where you have a bunch of app chains, maybe hopefully a bunch of Cartesi machines running on top of a shared sequencer? What does that future look like? Maybe Carsten, you can start, and curious about Benedict and Jeb's thoughts as well.
I think it changes around a lot, kind of like how we are interacting with, let's say, app chains, because right now there's kind of like the expectations that rollups have to include every single functionality. Like, let's say, you can deposit money into it, and you have to, let's say, bridge it out, back out again. You need to basically add in the logic, and basically programmers are traditionally not very good at building banks in their code. And things like shared sequencing could essentially mean that I could swap an asset that exists inside my chess game, whatever, together with a transaction that happens in something that's specialized in, for example, handling, let's say, more monetary value, or even, let's say, I think basically the space is, let's say, endless in terms of how these different things can be composed together. Of course, let's say, it's not as tightly connected together as, for example, let's say, a transaction on EVM, but I think that there's a lot of very interesting possibilities possible here. What I think in general is that the developer experience will change completely, because essentially to keep track of a block, essentially just need to synchronize essentially to the Espresso network and basically download the transactions that matter for your particular rollup. And as I said, that I, like they also said that I could start sending transactions to my little Rickroll VM without permission. And I think that changes around massively how infrastructure will rollup, the ease of development things. There's no reason why in the near future that we can't take a Docker container, maybe even broadcast it out to something like the Espresso network, have it deploy itself as a roll-up, and everybody can kind of follow it from there.
Carsten should write our marketing pitches. I mean, I couldn't have said it much better.
Well said.
Yeah, exactly. I think, exactly this sort of interoperability, the way you describe it, where suddenly it's much easier to move assets between rollups, is exactly the future that we envision. And, sort of the ease of deployment aspect. I think this is what Cartesi enabled so beautifully, right? Like that, you can, we can actually finally get to a world where you write an app, not in some weird, super low powered Solidity smart contract, but like you actually write a Linux application and you can run it on a public decentralized blockchain. That's exactly the future. I think that's sort of we're all working towards.
Jeb, do you have any thoughts as well? Anything to add?
Not really. Karsten and Benedict kind of nailed it.
Yeah. Definitely. No, super cool. I think we can open up to questions from the audience. We have 5 minutes left. And in the meantime, while we wait for questions, if any come in, maybe Benedict and Jem, if you guys want to mention the Rick Roll episode, like how it, like the unfolding of the after it was deployed, like what happened there. I think that was quite funny as well. Maybe we can to bring a bit of context.
Yeah, it was very funny. Just emblematic of the kind of stuff that happens on a test net. We have Carson here doing things that have never been done or hardly even conceived before. And it ran into a component of our system that was, to put it frankly, needs to be replaced and is being replaced. But it ended up kind of interacting badly with another rollup, the Vienna. It's an optimism stack rollup that was also running on the same testnet of the sequencer. We had this kind of weird interaction where there's a proof generated by the sequencer that kind of demonstrates. It basically gives you all of the transactions within a block that belong to your particular rollup, and it so happened that the proof for the Vienna rollup for this particular block ended up including a transaction from the other rollup, the Cartesi rollup, that was a 17 megabyte video transaction. Yeah, the Cartesi VM handles these 17 megabyte transactions no problem. The Optimism VM, not so much, right? Because it's trying to deal with like smaller, much smaller EVM transactions. So it's just this funny thing where like this like completely unrelated rollup suddenly stopped working, and I was trying to figure out why, and like looking through like raw block data and like found this block that was 22 megabytes large. Like, what in the heck is going on here? And then I remembered that Karsten was testing out Rick rolling videos, and kind of pieced together what had happened. So yeah, it was good. It found a bug, and we fixed we handled this now in our Optimism integration, which is great. But yeah, just goes to show you weird things can happen when you start pushing the boundaries. It's kind of exciting to see that.
Definitely, I think it'll go down in history. It's an important event. I'm curious, what's next for Espresso and for Espresso and Cartesi? Maybe Jeb or Benedict, feel free to jump in.
Yeah, so for Espresso, we have our next testnet coming out in early December or maybe late December. I think the exciting thing about this next one is it's going to be the first testnet where we actually have like third parties running some of the nodes. So we're really moving towards that kind of decentralized vision. And we're also starting to bring in a lot of the super high security features like the verified information dispersal that we talked about earlier. Yeah, looking to get to feature completion and be ready to go for mainnet sometime next year. So it's gonna be an exciting next few months, I hope, for Espresso.
Yeah, 100%. Karsten.
I can maybe just add a little bit what we're doing kind of on Cartesi side in this regard. Like we're kind of like continuing to kind of like experiment with like beyond just a video tool things, like experiment with what can we do in terms of easier deployment. How does this new world of a sequencing and requiring archives and fork proofs and arbitration and all those kind of things, how does it all match together? And at least I'm personally hoping that we can get Cartesi to a point where it's like uploading something to like like uploading to AWS Lambda, Heroku, or something like that in terms of ease and approachability for people. Because I think if we really make it possible for people to easily start using the power of blockchain and, let's say, high level amount data availability, I think that's when we'll see the real creativity happening in this space. And not just the economic ones, but also kind of like real practical ones. Like, at least I feel tempted to do something like, let's say, decentralized journalism, which might also be a source of kind of like populist videos and those kind of things. So, I mean, all the kind of crazy stuff that people actually want to build back then, but was kind of hindered by.
I love that. Yeah, verifiable, AWS. Yeah, I think a lot of cool stuff coming up. Sweet. I think we're running basically to the end of this call. It was awesome having everyone on. Benedict, Jeb, thanks so much for joining in. Carsten as well, as always. Yeah, if anyone has questions, feel free to ask them on the Discord. I think we're all around. And yeah, thanks everyone for joining and listening in. Have a great rest of the day.